So let's talk about what it means for a sequence to converge to a limit. And if anyone asks you what calculus is about, it's about limits. That's the study of limits is what calculus is all about. So it makes sense that we want to talk about the limit of a sequence. And this sequence can start at 0 or it could start at 1. It doesn't really matter. What this talks about is how does it behave as we get towards the end of the sequence, as our terms get closer and closer to infinity. So let's see here. I have this nice technical definition up here on the board. Let me interpret this for you with an example. So let's just suppose we're talking about the sequence. I don't know, let's do 2, then 4, then 2.9, then 3.1, and then 2.99, and then 3.01, 2.999, 3.001, so on and so forth. You can kind of see how these numbers tend to be closer and closer and closer to the number 3. So if I were to draw this on a graph, and it doesn't really matter whether this is the 0 term or the 1 term, but let's assume by default it's the 0 term. So at term 0, let me write out a few of these terms here. So for this sequence, 2 is our A0 term, which means at 0 we go up 2. Our A1 term goes up to 4. Our A2 term goes up to 2.9. Our A3 goes to 3.1. Then we have 2.99, 3.01. And you can kind of see how they're just kind of wiggling very, very slightly around the number 3. So 3 is going to be the limit of this sequence, at least it appears, unless something weird happens out here in the dots. But if it follows that pattern of bouncing above and below the number 3, then that limit should exist. And what all this says, this is a very technical way of saying that, look, epsilon right here is just a measure of closeness, all right? So this point is not close to 3 because it's not within that range right here between these two vertical, in this vertical space here. This point's also kind of far away. This point looks like it's just below, but eventually you can see how these points here are getting closer and closer until you could barely tell a difference between 3. And that's because when the epsilon gets very small, if the epsilons are very small, then the values of the sequence are very close to the limit 3. L is equal to 3 in this case. All right, but all this to say, if we're looking at the first few terms of a sequence, we could get a good intuition that these numbers are going to limit to 3. At least it appears like it. And for now, that's going to be good enough for us. So let's do a couple of examples where we're going to guess at the limit of a converging sequence. Okay, so we're going to guess the limit of a sequence known as the harmonic sequence, and we're just going to do that by writing out the first few terms. So, what is the harmonic sequence first of all? Notice that we have to start at the number 1 because we'd be plugging into the bottom of the denominator. We can't plug in a 0. So the first term is going to be given by plugging in 1, 1 over 1, then 1 over 2, then 1 over 3, then 1 over 4, 1 over 5, so on and so forth. And in fact, if you want, you can write out these terms. 1 over 1 is 1. This is 0.5. This is 0.3 repeating. This is 0.25. This is 0.2. And we need a few more terms, but you can kind of see how, since these denominators are getting bigger and bigger and bigger, eventually down the line we're going to have 0.01 when we divide by 100. Eventually we're going to have 0.001 when we divide by 1,000. And you can see how these numbers getting closer and closer to 0. And so the way that we write this, by the way, is that we say the limit as n goes to infinity of 1 over n is 0. And that means that the harmonic sequence converges to 0. The harmonic series, which we'll learn about later, does not converge, and we'll see why that does not converge, but the sequence itself does. All right, let's take a look at another example. So, new sequence, we're going to write out the first few terms. So let's see what we got here. And notice that it doesn't even tell us where we start, and for limits, it doesn't matter the first thing that we start at because we only care about what happens as we go out to infinity. Now, that said, we should just go ahead and assume we're starting with a 0, so we'll do G0, then G1, then G2. So these are the GNs where n starts at 0, but you could start it, if you prefer plugging in 1 first, that would be fine as well. It doesn't matter, but let's plug in 0. 2 to the 0 over 2 to the 1. Plug in 1, we get 2 to the 1 over 2 to the 2. 2 to the 2 over 2 to the 3. 2 to the 3 over 2 to the 4. It's probably, maybe that's enough terms there. We got, that's 1/2. This is 2/4. This is 4/8. And this is 8/16. Let's see, what does that look like it's doing? Oh, this is a very silly sequence, isn't it? Notice that it could actually be simplified. All these numbers become 1/2, 1/2, 1/2, 1/2. Okay, so of course, this sequence, and we might use an arrow to show this, converges to 1/2. Or we could write that the limit, as n goes to infinity, of 2 to the n over 2 to the n plus 1, that equals a limit of 1/2. And of course the reason is that way back at the beginning, hey, that's the same thing as 2 to the n over 2 times 2 to the n. Those cancel to get 1/2. And so, of course, every term of the sequence is 1/2. Now, what happens if a sequence doesn't converge? So that's what we call diverging. So diverging here in this question simply means, does it seem to not be converging? Okay, so let's take a look at the first few terms of this sequence right here. And again, it doesn't really matter where we start, but by default, I'm going to start by plugging in 0. So I've got -1 to the 0, 1/2. And then we've got -1 to the 1, 2 over 3. -1 squared, 3/4. -1 to the 4th, 4/5. So on and so forth. Okay, what do we got here? The even powers of 1, excuse me, this term right here should be -1 to the 3. And then 3 plus 1 over 3 plus 2 is 4/5. Excuse me about that. All right, the other ones are negative. So we get 1/2, -2/3, 3/4, -4/5. Of course, we could keep going, 5/6, -6/7. And here's the thing. It looks like these terms are getting closer and closer to 1, but these terms are getting closer and closer to -1. And since we have these terms, it's kind of flipping back and forth. We could draw a picture of this on a graph if we wanted. The first term goes to 1/2. The second term goes to -2/3, then 3/4, -4/5, 5/6, so on and so forth. You can kind of see how things are going back and forth, back and forth, back and forth. There's no convergence here. These are not going to converge anywhere. So we're going to say that since it doesn't converge, it diverges. Now, these sorts of things, these arguments might seem familiar, and they should, because in Calculus 1, you did a very similar thing. You dealt with limits. Speaking of which, we could say that the limit as n goes to infinity of the sequence Bn does not exist. or DNE, as some people abbreviate it. And we dealt with limits of sequences all the time in our calculus course. And so our Calculus 1 course, we can use those techniques that we use for functions and the limits of functions. We're going to learn how to use those for the limits of sequences as well.